All right, so we are continuing on with Learning Guide 6, moving on to Lesson 2, which is talking about acceleration. So in Lesson 1, we talked all about a position time graph and velocity, and how velocity was the derivative of our position time graph. So remember, velocity was the derivative of our position time graph. What we're talking about now is acceleration, which is one step further. And we're going to talk again about instantaneous acceleration, because obviously that's going to allow us to see what's happening at a specific time. So first thing we want to recognize is that acceleration is the slope of the tangent line on a velocity time graph. So think about what that means. I'm not talking position anymore. I'm talking acceleration is the slope of the tangent line. So think about slope of the tangent line on a velocity time graph. So guys, what are we talking about here? Again, we're talking derivative, right? So that must mean the acceleration is the derivative of the, not the position time graph anymore. It must be the velocity time graph. Okay. So if we know that, if we're talking velocity time graph, this must mean that our acceleration is going to be dv over dt. And it's the derivative of velocity, which means it must be the second derivative of my position time graph. And just as a little note for you guys, the units for this one are going to be meters per second squared. And I can see I've got a, sorry, I'm just going to do this board really, really quickly. Sorry about that. So again, I'll rewrite that. Meters per second squared is going to be our units. Okay. Now, we talked already in that first learning guide, or I'm sorry, the first lesson, we talked about how the first derivative identified slope. Now, remember, guys, second derivative on a regular graph identifies concavity. And we'll look at a diagram of that in just a couple of minutes. All right, so this first example, just to kind of put all this together here, the position of a particle is given by this function. So that's our position time graph with s meters and t in seconds. Find the acceleration at 3 seconds and 5 seconds. So we can't just find acceleration off the bat. What we need to actually do is find our velocity first, because velocity, sorry, our velocity is going to be our first derivative. Now, our first derivative is obviously just going to be 3t squared minus 12. And that would mean that our acceleration is the second derivative. So that's going to be 6t. Okay, does that make sense so far, hopefully? Now, if I'm looking at 3 seconds and 5 seconds, well, obviously that's what I'm going to be plugging in. So first of all, 3. So 6 times 3 is going to give us 18. Now remember, we're talking acceleration. So our units are going to be meters per second squared. Next one, 5 seconds. 6 times 5 is going to give us 30. And again, meters per second squared. So those are going to be our two accelerations at those specific times. The next question, find the acceleration when velocity is 0. So it's saying when, so obviously I'm looking for a time there. So when velocity is going to be 0. And I've got this equation already figured out. So we have our first derivative, and we're looking to see when is that equal to 0. So we're setting 3t squared minus 12 equal to 0. So when we solve that, add our 12, divide by 3, square root it. Now, obviously, that's going to give us positive and negative 2, but remember, we're talking time, so we're only looking at 2 seconds. okay, positive 2. And it's saying find the acceleration. So right now, at 2 seconds, our velocity is 0. So our acceleration, which is our second derivative, okay, which remember we figured out right here, we want to look for that when it's 2 seconds. Okay, so that's going to obviously give us 12, and our acceleration would be meters per second squared. Okay. All right, on the next one, whoops, sorry about that. On the next one, we are just looking at a visual representation of what we've got here. So acceleration on a position time graph. Now remember, position time graph is our original one that we were talking about in that last lesson, where velocity was our slope. So remember, velocity is slope, and that must mean that acceleration must be our concavity. Okay, because concavity is that second derivative. So if I look at this graph here, okay, if I kind of identify just from A to B to start off with, I obviously have a negative concavity there. So that must mean A to B is going to be negative acceleration. From B to C is again a negative acceleration. From C to D, all of a sudden, my concavity is now becoming positive. So from C to D, I've got a positive acceleration. Same thing from D to E is going to be positive acceleration. From E to F, negative. And look at F to G. What's happening there? Well, we know that that's a negative slope, but does it have any concavity? No, it doesn't. So we would literally just say a 0 acceleration. It's a constant. For the position time graph shown, again, it's position time graph, describe the motion. Now you can see we've got a little table here. This is a very good place to pause, try it yourself, and then fast forward to see the answer. I would suggest you guys do that. So our velocity, remember, is our first derivative, and our acceleration is our second derivative. And remember, this one is talking slope, this one is talking concavity. Okay? So from A to B, our velocity, well, obviously the slope is a positive, and our concavity is also going to be a positive. From B to C, we have a positive velocity, positive slope. However, we have a negative acceleration. C to D, I know my slope is a negative as well. My concavity is a negative, which means acceleration is negative. From D to E, my slope is still negative, but my acceleration has to be a positive. From E to F, again, positive slope and positive acceleration. And F to G, I've got a positive slope. However, it is a constant, so therefore there is no acceleration. So to summarize so far, and again, a lot of this you can see is quite logic-based. If A is greater than 0, then the graph is going to be concave up. If A, or acceleration, is less than 0, then on the graph there is a concave down. Okay, and if A is equal to 0, then on the graph there must be a straight line. Okay, now this little table I find really, really handy. I always go like S to V to A, just so that you can remember what's the first derivative and what's the second derivative, because I find sometimes students can get those a little bit mixed up. All right, so let's look at an example here of putting this all together. The position function of a particle is given by this big function, where t again is in seconds and s is in meters. Find the velocity. after 4 seconds. So remember, velocity is my first derivative. So again, s to v to a. I just find that really handy. So first derivative. Well, let's see. First derivative, the nice thing is all these derivatives are pretty easy. So 3t squared minus 12t plus 9. And it's saying after 4 seconds. So that must mean we're plugging in 4 for our t. So 3 times 4 squared minus 12 times 4 plus 9. And when you guys evaluate that, which you're more than capable of doing, you're going to get 9 meters per second. So at 4 seconds, the velocity is 9 meters per second. Find the acceleration after 4 seconds. So remember, acceleration is our second derivative. So the second derivative we need to find first. And so we're taking a look at this guy here, which is going to be 6t minus 12. And again, we're going to plug in that 4 seconds. So that's going to be 6 times 4 minus 12. And again, you guys are capable of doing that on your own, and that's going to be 12 meters per second squared. Okay. All right. When is the particle at rest? When is the particle at rest? So first you're going to need to think, okay, well, what does that mean specifically? What does that mean when it's at rest? Well, when it's at rest, we've basically got a velocity that must be equal to 0. Okay, so that's important. So remember, velocity was our first derivative. So when is that going to be equal to 0? Well, I've got 3t squared minus 12t plus 9. And we want to find out when. So obviously we're looking for our time here. So we're going to have to factor. So let's get rid of that 3 first. Oops. And I want to rewrite it for some reason. T squared minus 4t plus 3. Okay. Looking at this one, this is a good way to factor here. We've just basically got our, sorry. Okay, so we can just look at the factors of 3, so that would be negative 3 and negative 1, that are going to give us negative 4. So we've got 3t minus 3 and t minus 1. So therefore, because we factored it and we want to solve for our t is going to be equal to 3 and 1. So when is the particle at rest? Well, the particle is at rest at 1 second and 3 seconds. Okay, so the important part of that question definitely was, when is the particle at rest? Thinking that must mean that our velocity is equal to 0. All right, let's continue on with this question. We've got a few more, and then that's it for this lesson. Again, we've got the same function. It's saying, when is the particle moving in the positive direction? So positive direction, that must mean that our velocity is greater than 0. And again, if you're not too sure of that, go back to that first lesson. And I mentioned, if the velocity is positive, it's moving in a positive direction. If it's negative, it's moving in a negative direction. So what we're going to actually use here is the idea of maximum and minimum. And this, again, I'm going to bring in our second derivative test. Because remember, guys, if I have let's say a maximum here. Well, I know that this is a positive and this is a negative, so therefore it would be really easy for me to say, well, it's moving in a positive direction here and a negative direction here. This just kind of gives us a visual representation of this graph. So we're talking about velocity here, and we've already got our velocity function, which is this. And we already, in that last question, figured out what our critical values were. Remember, our critical values were t is equal to 1 and t is equal to 3. Okay, so basically, I know 1 and 3, something is happening here. And we also know that I've got my 0 there. Has to be my critical value as well. Okay? So this is where we want to bring in that second derivative test. Okay, and second derivative test, I obviously need the second derivative. So the second derivative, remember, was 6t minus 12. And the second derivative, remember, all we need to do is plug in those critical values, and we need to figure out what our graph is doing. Do we have a maximum or do we have a minimum? So first I'm going to plug in the 1, which was my critical value there. And so that's going to be 6 times 1 minus 12 is negative 6. Now remember, I don't care about the 6. All I care about is that it's a negative, which tells me my graph is going to look like this, which tells me that I've got a maximum point at 1. So I know my graph is going up here and it's going down here. So hopefully 3, we're going to get the opposite. So let's figure that out. So 6 times 3 minus 12, that gives us positive 6, which is great because that means that we've got a happy face, which tells us that we've got a minimum here, which makes sense on our graph. So that must be going up again. So looking at this, the question is saying, when is the particle moving in the positive direction? Now the positive direction means I must be having a positive slope. So there and there. So we can say from 0 to 1 second, we're moving in a positive direction, and 3 seconds, and I can even just write here, greater than 3, or 3 seconds onwards. Okay, so when the time is greater than 3. Okay, so hopefully that makes sense to you guys. If we move on, it's saying find the velocity when the acceleration is 0. So this one doesn't take too much thinking. This is just kind of more calculation based. So again, find the velocity when the acceleration is 0. Well, remember, acceleration is that second derivative, which is 6t minus 12. When is the acceleration 0? So obviously we're looking at this time. So add in our 12. So t must be equal to 2. Well, when is the velocity, or what is the velocity when t is equal to 2? Remember, that's our first derivative. So 2 squared minus 12 times 2 plus 9. And when you guys evaluate that, again, which you're more than capable of, I'm going to get negative 3 meters per second. So I know my velocity is going to be about negative 3 meters per second. All right, and the last question on this lesson is find the total distance traveled in the first 4 seconds. So we did a question very similar to this one in that last lesson. Again, what we need to think about is kind of our table here. Again, and looking at our critical values, because remember, whenever we have a critical value, something is happening. It's either changing direction or it's stopping or something's going on. So we need to figure out what the distance is in each little interval. Now remember, we have to start at 0. Our first critical value is 1. Our next critical value is 3. And then it's saying in the first 4 seconds. So obviously 4 is going to be a critical value as well. This one, if you recall, a critical value, if I'm looking for distance traveled, I need to look at the original question. I need to look at that original function to find what an actual distance is. So no derivatives in this one. So the first, for the first one, we're going to have s of 0. Now again, you guys can do all of these calculations on your own. This one's pretty obvious. It's just going to be 1. S of 1. Again, is going to be 5. And all you're doing is plugging that into your original equation. S of 3 is going to be 1. And S of 4 is 5 again. Now, thinking back to how we did that last question in that first lesson, remember how we had S2 minus S1? And because we're talking distance, we know our answer is going to be positive regardless. So we're going to have our 5 minus 1 plus 1 minus 5. So all I'm doing is just subtracting the previous one, right? Plus 5 minus 1. And that's going to be equal to our total distance. Well, 4 plus 4 plus 4 is going to give us 12 meters. So the particle has traveled 12 meters in the first 4 seconds. All right. Now, this kind of stuff I found in the past can get a little bit confusing. So I really encourage you to do your homework. Make sure that you guys are understanding that. And as always, visit the help desk if you have any questions.